And let's hit from current slide. One additional announcement, or a couple of announcements, that have to do with my office hours. Today, my office hours, at least as far as I know, will be as normal. After this class is over with at 3:15, I'll be here at least until 5:15. And with all these papers to grade, I may be here, well, past 5:15, but at some point I'm going to run out of gas because I've been at sleep deficit all week and getting worse every night. So at some point I'll have to quit and go home. But I will be here unless something happens, health-wise or something that I really feel lousy or something. I'll be here at least till 5:15 and probably well after that. Okay, but tomorrow office hours are a shot, okay? We have the Honors and Awards Day ceremony from 10 till 12, which doesn't, well, that in itself would mess up office hours some. But the fact that they're on the Birmingham campus is one thing, and they require us there way early is another thing. So, but it really doesn't mess with office hours because normally I have a class in. But I'm going to meet with my 8 o'clock class and probably meet at least until 9. But between 9 and 9:15, I'll have to end the class and head over to Birmingham campus. Okay, so that will be tomorrow morning. Normally, my office hours would be 10:45 to 1:15, but because the Honors and Awards ceremony is going to go at least through 12, and then it's going to have a half hour back here, then I don't anticipate being here much before 12:30 and probably after that. So I only have about 45 minutes of office hours, if that, from 12:30 until 1:15. So that's tomorrow. And then at the end of that class, 1:15 is 5:45, and I'm getting out of here as soon as I can. Okay. Then Friday, normally I have office hours on the Birmingham campus, 7:45 until 1. But not Friday, because this Friday I have an infusion, and it starts at 8. I need to be there by 7:45, so I won't be on campus at all in the morning, and usually the infusion goes at least until 4:30, or somewhere around 4:30. So I won't be driving back to campus after that either. I won't be in much shape to drive back to campus because of the Benadryl and the Tylenol they give me and stuff like this to keep down reactions. I need to drive home and get to bed, or relax anyway. Don't need to be on the road. Okay, so that messes up office hours for the rest of this week. Next week, as far as I know, they should be fairly normal, whatever that is. Okay. Yes.
Do you know what is the American University and College?
The what? Okay, can you say the name one more time?
American University and College.
Something University and College. American University and College. I don't know things about that. I know there is an American University in Washington, D.C., I'm pretty sure, because that's where one of the shows used to be the Diane Rehm show, which is now the 1A is the name of the radio thing on NPR, is out of American University in Washington, D.C., but American University and College, and they're supposed to be somehow connected to Boston.
It's something like, I don't know what is that. I have no idea.
Frankly, to me, it almost sounds like a scam. Okay, it may not be, but it almost sounds that way.
And the Lawson State, like it says, they nominate 151 students.
You got it came in the mail?
Yeah.
And it said you were one of the 151
Yeah.
students? Okay, I got that too.
What is that?
It said if you go in and make a profile on the website, you were eligible for one of the 3 scholarships.
Okay.
And I guess I don't know how they pick who gets.
What my guess is they're fishing for your personal information. Is what my guess is. What I would do, I would bring, if you have the letter, bring it in to someone here at the college,
Yeah,
and let them look at it.
who's who
Yeah,
amongst students.com.
Okay. Now that may be something else. That may
It
not
said
be
they
that.
put out a magazine, I guess it was, that acknowledges you were one of the people in the.
And for giving away your private information, you can have your name listed in our
I'm not
magazine.
giving you that.
What a deal, you know? Yeah, I don't know.
They had They had all my information already. So.
Oh, really?
Yes. So they have my student email and all my name and address. So.
Oh, you tried to.
I did. I went in and it gave you a number
Yeah.
and password
And username
to
and
go
password.
in and make an account on this website.
Yeah.
So I went in. I just put in the number and yeah, it had my name, student information. So it might be something legit.
It might. I would bring it in and have someone look at it. I would not trust it until it had been. But there are these things to do. I got something. If I pulled up my email and remembered the name to look under, there's this outfit that wants to recognize us because they've heard of our great success in doing what we do and recognize us and give us an award, okay, institutional award. And I only have a short time left to agree to do this, you know. I've been receiving these for months now. But it's sent to Bessemer State Technical College. And we haven't been an entity
My dad
since,
was there.
yeah, he went here, an entity since 2005. And yet this is they've heard how great we are, blah, blah, blah. Yeah, right, okay. And I get them a lot on, you know, you've been recognized as a blah, blah, you know, leader in your field type stuff. Just send us your information. And with no obligation to you whatsoever, we'll issue blah, 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 blah. I usually just throw them away. Now, there are who's who. You know, there is such a thing as that. And this may be the legitimate one, and it may be a knockoff that's trying to sell you something. And if you'll just buy the brochure.
They are trying to sell you.
Oh, really?
Brochure.
Wow, what a shock.
Do what?
They are trying to sell the book.
Yeah, they said that you can pre-order the book and get a special spot in it instead of just your name and regular.
And what do you call they have a list of cards. I mean, you can buy things, right?
I didn't go in that far. I just saw that they were
No,
trying to
it's
sell
just
it.
a leaflet. They have
Yeah. It's not. It's just a little pamphlet, I guess. That
Yeah.
has your name and something.
Yeah. And I said it for your benefit, but now I'm beginning to want to say it for the college's benefit, because if they have all your information, I wonder if they somehow got into the college's account. And if they did, we need to know about it.
Yeah.
So if you don't mind, please bring that information. And I will get it to somebody and have them look into it. Especially when you said that about they already have.
Yeah, I got the same letter she got.
Yeah, but that you went in and they already had your
Yeah.
lots
It
of
gave you
information on you.
like a unique number to log in
Right.
with a password, and I typed that number in and it had all the names and stuff
Yeah.
already.
So I would be that makes me concerned that either college provided that, which I think is pretty bad, or somehow they hacked in and got it, which I think is pretty bad. So I don't know which is worse, but they both pretty bad. So I would encourage you to do that. And I've been meaning to tell all my classes this, and it just dawned on me to say it now. As far as I know, I saw something in the email recently that I think the student course evaluations are now open. They are. Okay.
I got my email letter.
Oh, I didn't.
Okay. So if you will, whenever you can wait till as late in the term as you want to, but don't wait until you leave town, okay? So try to get the student course evaluations done. Okay. Any other questions before we get started today? Okay. Let me turn on the projector. And we just started 4.3 last time, and we're talking about homogeneous linear equations with constant coefficients. These are fairly easy, and I found them absolutely sort of fun to do, okay? So, let's start the case, special case of the second order equation, okay? AY double prime plus BY prime plus CY is equal to 0. Okay? Now, as we did last time, right at the end of the time, we saw that certainly for first order linear differential equations with a constant coefficient, we knew that y is equal to e to the mx would certainly fit every one of those and give us the solution. Second order, third order, nth order, the suggestion is it still will work. So let's try it and see. Now a, b, and c are constants, not functions. Okay, no dependence on the variable x or y. They're just constants. So we're going to try to find our solution, and what we try is y is equal to e to the mx. Now why they choose m, it's sort of arbitrary, but lots of people use it, so why not? Now if your independent variable was t or something else, it'd be e to the mt. You know, whatever your prime is deal with, and written in prime notation, you don't know what that independent variable is. Whatever it is, that's the x up, the variable up there. Okay. Well, if y is equal to that, that's your guess, okay? Then you give me, what would you do with that? Y, you take the derivative, you got it. And what would that be? M e to the mx. And then on this one, we'd have to do once more and do y double prime would be m squared e to the mx. Then if you plug this in, you get a m squared e to the mx plus b m e to the mx plus c e to the mx is equal to 0. Right? Very similar to what we did last time. Got it? Now, all these have a factors of e to the mx. So let's factor that out. E to the mx times am squared plus bm plus c is equal to 0. Right? Can e to the mx ever be equal to 0? No. Exponential function approaches 0 as x gets very, 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 very negative. Unless, of course, m is a negative number, and then as x is very positive, it's approaching 0, but never gets there, ever. Okay? That's always positive. Maybe slightly positive, but it's always positive. Never could be 0. So that means this has to be 0. am squared plus bm plus c has to equal 0. And if you had that as the case, especially if you don't know what those coefficients are, remember a, b, and c are constants, what would you use to solve that equation? Quadratic equation? Quadratic formula. M is equal to minus b plus or minus, and this is even a, b, and c just like we're used to seeing. So we can come up with the values for m. Now those values for m could be integers, they could be rational numbers, they could be irrational numbers, or they could be complex numbers. And over the course of the rest of the sections, or this section included, we'll cover all those possibilities. Okay? But there you have it. So whatever those m's are, this one would have how many solutions? up to 2 unique solutions. However, you could have a repeated 0, and then you'd have another case, and we'll talk about that case. If M is complex, then both of the M's will be complex. They'll be complex conjugates of each other, and we'll look at that case. If they're irrational, they'll be conjugates of each other, irrational conjugates of each other. We'll see that case too a little bit, not so much. But otherwise, they'll be real numbers, whatever they are. Okay, this is called the auxiliary equation. Okay, that's called your auxiliary equation. Whenever you have a homogeneous linear equation with constant coefficient, you're going to have this as your, and you don't have to go back and do the y's. It's a good idea to, but the thing is, you can just write that down. Whatever your derivative, the degree of your derivative is here, that would be your m squared, m first, and those are your coefficients. And your variable is going to be m, right? And you come up with whatever. Now, if you have third order or higher, then you have to go back to what we used to do, what you did in pre-calculus algebra when you found the zeros of polynomial functions, okay? And you go through all that process. Rational zero test, you know, and Descartes' rule of signs, and upper and lower bounds, and synthetic division. You remember that fun stuff, right? You get to use it again. Isn't that wonderful? Okay. So, in general, this one that we're talking about here, and I started on this but then got into other things here, you can use the quadratic formula and it'll give you 2 solutions. One solution will be minus b plus or minus the square root of b squared minus 4ac. We even use a, b, and c. That makes it so easy, over 2a. Whatever those coefficients were, there's one, I'm sorry. Okay, one is plus and the other m2 is minus. Minus b plus or minus, I do it every time, I'm so used to doing that. This time it's going to be minus the square root of b squared minus 4ac all over 2a. Those are your 2 solutions. Okay. Now, as I said before, I sort of was talking just in general, if M1 and M2 are both real solutions, that means they could be integers, rational numbers, or irrational numbers. If they're irrational numbers, they're going to be in conjugate pairs, right? Plus or minus square root of 17, something like that. Plus here, minus there. They'll be in conjugate pairs, okay? Unless, of course, these coefficients they can be constants. If they are irrational numbers, then they won't necessarily be together. So you know that fine, okay? But they'll give you 2 real solutions if they're distinct. If, however, this thing here, remember your discriminant, if this happens to be 0, then you have minus b over 2a. It's a double root. And that means they won't be distinctly different. They'll be the same. Well, then we'll come up with another way to deal with your second solution. And it'll be simple. You've seen it before. Okay? And then the other possibility was this thing being negative. If that thing's negative, then you get 2 complex solutions, and we'll talk about that later. But if this is positive, you get 2 distinctly different solutions. If it's 0, you get a multiple solution. So this will be 1 minus b over 2a, and the other one we'll talk about. And then, if this is negative, then you'll get complex solutions to that, and you'll get another type of solution. Okay, so let's look at each of those. Okay? Let's do distinct real roots. Okay? distinctly different but real roots. So, just like I have here. Under the assumption that the auxiliary equation has two unequal real roots, m1 and m2, we find the solutions to be y1 is equal to e to the m1x, and y2 is equal to e to the m2x. Okay? And they have their coefficients in front, c1 and c2. You know, unless you knew what those were, you have your arbitrary coefficients in front. Two possible solutions, okay? Well, actually, I was jumping ahead. Leave that blank for now. Those are your two possible roots, and then your general solution would be y is equal to c1 e to the m1x plus c2 e to the m2 sub 2x. Okay, if my pen will ever catch up. Okay, it did. All right, there's your general solution. If you have two, for your auxiliary equation, you have two distinct real roots. Now that means the discriminant here is positive. Now if that discriminant happens to be a perfect square, then those are going to be rational roots. If it's not a perfect square, there will be irrational roots, but no matter, as long as this is positive, those are going to be two real roots. Okay? Now, that's the first, two distinctly different real roots. The second case is what if they're repeated. In other words, the b squared minus 4ac is 0. Then you just have one solution, m is equal to minus b over 2a. And certainly one of your solutions then, y1, would equal to e to the minus b over 2ax, if that's your variable. Okay? But you need a second solution. Okay? Well, what we do then, if you go back to 4.2 and you follow that along, the equation 5 in section 4.2, and you can go back and look at it, there is a second solution, and that y2, and this will just about always be the case, x e to the minus b over 2ax. Okay? Now, they're calling this m1 to keep from having the right minus b over 2a. So y1 would be e to the minus m1x, and y2 would be x e to the minus m1x. Okay? So you just take the one solution you know and then put a coefficient of, not a coefficient, the variable x and multiply times e. So, the third case, what if the discriminant is negative and you get complex numbers for your solution for your auxiliary equation? Sort of a big boo hiss here, right? Well, let's see what we can do. So if m1 is complex, now, as long as your coefficients are real coefficients, if you have a complex root, they'll come in ordered in conjugate pairs. Now, if you have complex coefficients, those bets are off. Okay, but if they're real coefficients, then you come in this. So your m1 then would be alpha plus I beta. Okay? Now, you didn't really have alphas and betas there, but whatever you get your answer to be is a real part and an imaginary part. let's go back. Remember, your M1 was minus B plus or minus. Do it every time. I'm so used to doing that plus or minus. Okay. M1 was plus. Okay, plus the square root of B squared minus 4AC over 2A. Okay? Now, if this thing in here is negative, the discriminant is negative, then what your M1 is minus B over 2A. That's your alpha. That's the real part. Plus, and then whatever that negative number is. Okay? It's a negative number under a radical. So, whatever the real part of that negative number is, if this is negative, B squared minus 4AC is less than 0. Not even equal to 0, less than 0. Then, minus 1 times 4AC minus B squared, that's the same thing, isn't it? Right? And that's under your radical, right? Because that was what was under the radical. Okay? Well, this part here is going to be your I. So your 4AC minus B squared is going to be your beta. Actually, the square root of that. The square root of 4AC minus B. 4AC minus B. Oh, wait. Yeah. No. Okay. That's going to be part of it. The other part of it is over 2A. Okay. Got that over 2A in there too. So, rather than writing minus B over 2A every time we want to do the real part, and the square root of 4AC minus B squared over 2A as the second part, we'll just name the alpha and beta. So it's a lot easier to write. But remember, that's what the alpha and the beta is. Alpha is the minus B over 2A. Beta is the square root of 4AC minus B squared over 2A. Because if this is complex, if there is an I there, then just factor out the minus 1. That's the square root of minus 1. That's the I. And then you reverse the order here, and that will be real. This will be a positive number now. If this was negative, if this was negative, that has to be positive, right? So this is the real number. So square root of 4AC minus BA, B squared, over 2A, that's going to be your beta. Okay. So there's your M1. Your M2, of course, would be the same alpha minus I beta and the same beta. Okay? Now, and alpha and beta, yeah. Beta is a positive number because, let's see, is that guaranteed to be positive? I know in the radical has to be positive. This is assuming the A has to be positive too. I don't know if they ever said that had to be true. They said A can't be 0, but if A was negative, then your alpha could be, the beta part, I'm sorry. No, yeah, that's true. If A is negative, that would make that, but don't sweat it. We'll just assume that beta is positive and real, okay? So, your general solution then will be y is equal to, and technically no difference in the first case either, except you have imaginary numbers in it. So that would be, and now they for some reason put capital C1. just to indicate that these, I don't know, just to distinguish from the other. E to the alpha plus I beta. And you see, back in pre-calculus algebra, they always put that beta I. I kind of like I beta better, but yeah, that's just a preference thing. Times x plus C2 e to the alpha minus I beta x. Okay? That would be your general solution. Okay? However, that's really awkward. To have an e raised to a real part times an e raised to, because that's what it is, you know, when you have a base and a sum here, you can make that e to the alpha x times e to the I beta x, right? That's the rule for exponents. You can do that, okay? And it just makes it a little awkward. In practice, we prefer to work with real functions instead of complex exponents. Don't you? Don't you like real functions better than complex exponents? I don't like complex exponents, okay? So to do to this end, we use Euler's formula. Okay, Euler's formula, and that's this. E to the I theta, okay, is equal to cosine theta plus I sine theta. Okay? Now you look at that and say, oh, big deal. Rather than having an I in the exponent of your E, now you have I as a coefficient of the sine theta. Are we any better off? Well, actually, we are a little better off. Okay? Now, theta can be any real number. Okay? And they give you a little derivation at the bottom of the page and let you play with that. And you see that is indeed true. Okay? Now, it follows from this formula, this is the magical part, okay? Remember we had e to the I beta x up here and e to the minus I beta x here. Remember that? So let's do that. E to the I beta x, okay, would be equal to cosine beta x, right, from here, e to the I theta, this would be cosine beta x, plus I times the sine of beta x. Okay, that's e to the I beta x from Euler's formula. Just rather than theta, we're calling it beta x. Okay? And in the other one over here, you would have e to the minus I beta x. And if you did that, that gives you cosine to the minus beta x, right? Okay? Minus, plus I to the sine of minus beta x. Okay? Now, because cosine is an even function, you can lose the minus sign there. Cosine of minus u is equal to cosine of u. So that's the same value. Sine, though, is an odd function. So sine of minus u is minus sine of u. So you could then change, well, I didn't want to do that. Yeah, I did want to do that. Make this a minus here. Ooh. It's not responding. Make this a minus here and make that a plus. Okay? Now, so, all right. The interesting thing to this is, what if you added these two numbers together? E to the I beta x and e to the minus I beta x. Okay? Because really, that's what you're going to do up here anyway. You're going to have a C1 e to the I beta x plus a C2 e to the minus I beta x. Forget about the c's for now, and you're going to add those two together. Well, what happens if you add those two together? You'll come up with 2 cosine beta x, and these two disappear. Guess what? There goes your imaginary parts. Gone. And not forgotten. Okay? Oh, we forgot them too. Okay? Who cared? Okay. Now, what if you had e to the I beta x minus e to, and you know, that could have come up to e to the I beta x minus e to the minus I beta x. Well, then, unfortunately, if you negate this and this by making that e minus there, you lose your cosines, and now you add this. This is equal to 2I sine of beta x. Okay? That's a big boo hiss because I didn't want the imaginary parts. Okay. And here is where they get sort of kinky in my book. They start with this. Since y is equal to c1 e to the I beta x plus c2 e to the I minus I alpha minus I beta x is the solution for any choice of constants c1 and c2. For any choice of constants c1 and c2. Why don't we choose c1 and c2 both to be 1, and c1 to be 1, and c2 to be minus 1, which in turn gives you two solutions for this. And the first of these solutions is I'm going to try to keep as much of this as or some of this, because I've been really flagrant. I hope you remember that. If not, we'll come back and recreate it. Okay. The book didn't go into that at all, but I was just showing you we didn't really make stuff up there. Okay. So what we had before was a y1 is equal to, and again they do, okay, but they're going to choose the c1 to be 1 and c2 to be 1. So this would be e to the alpha plus I beta x, okay, plus e to the alpha minus I beta x, whoops, there, started to put, okay. So there's your y1, and in the second instance, when you use 1 and minus 1 as your coefficients, we'll have your y2 is equal to e to the alpha plus I beta x minus e to the alpha minus I beta x. Okay? Now, this first one, based on what we did below, gives us 2 e to the alpha x cosine beta x. Okay? Now, I don't know if you followed that, but this result here, if you did this part, the e to the I beta x plus e to the minus I beta x, that's where you got this one, 2 cosine beta x. Where you put the 2 on the outside, put the cosine alpha on the inside. Okay, now, remember that? Okay, we sort of scaled over that. This is e to the alpha times e to the I beta x. Remember, alpha x e to the I beta x. So this comes from this part, and the combination of, and that's common in both of these. And since we use C1 and C2 to be 1, that was indeed common, both of them. And then the e to the I beta x times e to the plus e to the minus I beta x, that gave us this cosine 2. So there is a solution with no imaginary parts. There's your y1. Okay? Your y2, on the other hand, this one is equal to, you get the e to the alpha x, that's from this and this, okay? And then you get e to the I beta x minus e to the I beta x, and that's what we did here. And this is going to be 2I times the sine of beta x. Okay? 2I e to the alpha. Okay. Now, if you go back to theorem 4.1.2, which is way back there, I think in 4.1, yeah, near the bottom of page 120, okay, is superposition for it, and there's a corollary to that. That's the top of 121. The last two results show that e to the alpha cosine beta x and e to the alpha sine beta x are real solutions for your equation. Okay? Moreover, these solutions form a fundamental set on minus infinity to positive infinity, and consequently the general solution is, and I mean it seems like magic, they just lose the I. They basically lose it, okay? So your general solution here is y is equal to, with no i's left in it, C1, now we went back to being a small c, e to the alpha x, now remember what the alpha is? Minus b over 2a from what we had before, okay? Cosine beta x plus C2 e to the alpha x sine of beta x. Remember, man, just suddenly dizzy. These are all sort of running together, aren't they? Okay. So there's your solution, which can be written another way. I like it better this way. E to the alpha x, pull that out, and then in parentheses C1 cosine beta x plus C2 sine beta x. Okay? Yeah. Now, so even though you have imaginary solution for your auxiliary equation, you wind up with real solutions for your differential equation. Okay? That's the magic. Okay. Let's do example 1. Excuse me. I crammed down lunch way too fast today, and it's not sitting too well. Wow. Not well at all. Let's solve some differential equations. A. 2y double prime minus 5y prime minus 3y is equal to 0. Okay? Now, you can do the substitution if you want to, but if you remember the e to the mx, that's what you're gunning for, just finding out what the m is. What's your auxiliary equation you would use? Two m squared minus 5m minus 3 equals 0. Okay? Now, if we can, let's factor it. Don't know that we can. I have a real sneaking suspicion we can, but let's see if we can. So only possible factorization for 2m squared, I'm sorry. 2m times m. Sorry. It's getting harder to breathe. Now, what about signs? One's a plus, one's a minus, right? Got to be different signs because of that. Let's just try putting the plus here and the minus there. Now, possible factorizations for 3. 3 and 1. I'm going to put them here and here. Okay? That's because I'm cheating. I'm looking ahead at this and seeing what's going to do. Let's do this. Let's try. See if I cheated right. 2m times m is 2m squared, right? 2m times minus 3 is minus 6m plus m is minus 5m, and then minus 3. Yes. Got it? Take as many steps as you need to get it. I was just trying to eliminate as much as possible. So what do we get? M is equal to negative 1/2, or m is equal to 3. Okay? Now remember what our guess function was? Y is equal to e to the mx. Okay? So this gives us two possibilities. The first of these is called y1 is equal to what? A little louder, I can't hear. It's going to be E. Ooh, goodness gracious, my pen disappeared. Okay, it's going to be e to the minus 1/2 m, and your y2, e to the, I said m, x. Why do you let me write m? Okay. Goodness, I'm getting 3x. I'm going Lulu here. Okay, so what's your general solution? Y is equal to C1 e to the minus 1/2 x plus C2 e to the 3x. Okay. All right, I think that should do it. Yeah, y1 is equal to c1 e to the minus 1/2 x or minus x over 2 plus c2 e to the 3x. Got it. Okay. I hate to do this, but I'm going to have to put it on pause for just a minute and go clear my head and my throat because it's... All right, here we go back again. Let's do the B part. This time we have y double prime minus 10y prime plus 25y is equal to 0. What is our auxiliary equation now? M squared minus 10m plus 25 is equal to 0. Does that have a solution? What? M minus what? M minus 5 times M minus 5 is equal to 0. So what M do you get? 5. Only one solution, but you got to have two. What do we do in a case like this? Now remember what that stands for. That would be y1 then would be e to the 5m, right? By that? Okay. What would be your y2 then? Remember what happens if... What's that? Okay, x e to the 5. Why do I put m's there? Yuck. E to the 5x. Okay. This is driving me nuts. No. Okay. E to the 5x and y2 would be x e to the 5x. So what would be your general solution? Y is equal to c1 e to the 5x plus c2 x e to the 5x. Okay, so there would be your B, okay?
And why was that one x e to the, and not the first one too?
I've lost the page. Say that again.
On the A one, our y2 didn't do the x e thing, and on this one, the y2 has x in front of it.
Okay. Okay. Because if you go back to case 2 on page 133, this is case 2 repeated real roots. You had m equal 5 and m equal 5, right? So what's the result of that? Your C1 is going, or Y1 is going to be C1, well, they don't split it down, but it's e to the mx, m1x, plus x e to the m1x. Okay, you only have one m, 5, so it's C1 e to the 5x, and then the second one is C2 x e to the 5x, because it's a repeated root. Okay. Whereas the first one, you had two distinct roots, so each of them were just e to the blah, 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 blah. Okay. Now, the C part. Okay. I'm going to go to a clean page here. C part. Y double prime plus 4y prime plus 7y is equal to 0. What's your auxiliary equation? M squared plus 4m plus 7 equals 0. Any way you think you're going to factor that? Only possible factorization is 7 is 7 and 1. No way that's going to add up to be 4. Okay? So what will we use now? Quadratic formula. So m is equal to minus b minus 4 plus or minus the square root. Well, let's do, okay. I like to do plus or minus. The book likes to split them up. I'll split them up later. And what goes here? B squared, so that's 4 squared is 16 minus 4 times 1 times 7, right? Over 2. 2 times 8, right? Everybody buy it? So this is going to be minus 4 plus or minus the square root of 16 minus 28, right? Wouldn't that be minus 12 over 2? A big boo hiss, right? That would be minus 4 plus or minus. I'm going to factor out a 4 and an I, actually a 2, because 12 is 4 times 3, and the square root of 4 is 2, so that would be 2i times root 3, right, over 2. Well, this 2 will get rid of one of those and get rid of all of them. The square root of negative 1 is I, yeah. Okay? So this winds up being, here are my 2. M1 is equal to 2 plus I root 3, and M2 is equal to 2 minus I root 3. Okay? Now, what do we do with that? Okay? In this case, this is what we've been calling alpha, and this is what we've been calling beta. Alpha is 2, beta is root 3. Okay? And without having to go back and rederive Euler's formula and reuse it and do it all, let's just remember our result from that. Top of the page there, and what did that give you? Your y, your solution was, your final thing was, the alpha was the same in both cases, right? Oh, wait. That's a minus 2. Sorry. I didn't see my minus sign on my minus 4. Okay. Okay, so alpha is minus 2. So this is C1. Well, wait. Let's factor out the first. Okay. We factored out the e to the, so this is e to the minus 2x, right? That's e to the alpha x, right? If you look up at equation 8 above, the final thing is you factor out the e to the alpha x, okay? Times C1, okay? And they usually start with the cosine. And then the beta in this case is root 3. square root of 3, for some reason it's not writing, there it is, square root of 3x plus C2 sine the square root of 3x. Now be careful with that your square root sign doesn't incorporate the x, okay? I kind of like to, just to keep that from happening, write it cosine x root 3 sometimes, just to make sure that's it. And there's your solution. Without having to go anywhere else. You don't remember, I said this was minus b over 2a and stuff like this. It's already taken care of. You've already done those calculations. You don't have to worry about them anymore. That's your solution. With no imaginary parts. Even though it came up with an imaginary m, a complex m, you lose that when you write it in this form. Thank you, Euler, for giving us that formula. Okay? So there are their solutions. Now, do we have time to do example 2? I'm afraid not. Okay, so we'll begin example 2 next time. Sorry that I had to take a break in the middle. I just not feeling a lot, I am feeling a lot better. Drinking something really helped. So, exercise set 4.3. We did pretty good order on this to get this far. Any of the odds 1 through 13. Think you can do any of the, we haven't done higher order here yet, have we? Let's just stop there. Let's do 1 through 13. Odds 1 through 13. And next time we'll wrap up and move on to undetermined coefficients. Okay? A superposition approach or big long section there, undetermined coefficient annihilator approach. And basically what I think I'll do is I'll let you choose which one you want to do. We'll only do one of those. And you can always go back and figure out the other one on your own. All right. Any comments, questions? Okay. Let's see where we're standing in this course. I think I already mentioned it. It seems like I've got 3 papers in. That means I've got 3 people without turning in papers. Now 2 of those are trying to do it remotely. I don't know. I'll have to check emails to see if they sent. First test, I've gotten those from you, but I don't have them from the other 3 people. And second test, y'all got, right? Okay. I don't have any of those yet. Okay. Try to be wrapping up because we're running out of term fairly quickly.